In this video, we're going to cover where electrons are located around the nucleus, which is called the electron configuration. The atomic orbital is the space in the atom where the electron is most likely to be found. In the Bohr model, we represented orbitals with circles, but we're going to get to a more quantum type of model that shows us how energy levels actually have sublevels, and each sublevel is composed of an orbital that has a special shape. So we have 4 different orbitals, 3 of which we've got right here. Each orbital can hold 2 electrons, which is important for us to remember when we get down to writing the electron configurations. So our s orbital is the one that has a sphere shape. Because of the 3D nature of a sphere, there's kind of only one direction it can go in, x, y, and z. And so the s orbitals only hold 2 electrons. For the p orbitals, we call these a dumbbell shape, like the dumbbells that you might lift at the gym. The p orbitals, because of their shape, they can go in the x, y, or z direction. So you notice these little subscripts, you've got px, py, pz. And since they're kind of arranged in 3 different directions, the p orbitals, each one holds 2, and so total, that's going to be 6 electrons. And then the d orbitals, we say that these have a clover shape, and they're a little bit more complicated, but you've got 5 different directions of sorts, and so the d orbitals can actually hold altogether 10 electrons. So 2, 4, 6, 8, 10. When we're looking at the first energy level, remember you've got energy level 1, 2, 3, 4, 5, 6, 7. We're seeing that the first the first energy level holds 1 s orbital, like we have written here. The second energy level has an s and a p orbital. So you're reading the periodic table from left to right, and you're just gonna fill up those electrons based on whatever box you have for the element that you're looking at. In reality, these orbitals are gonna kind of layer on top of each other so that the electrons are flying all around, and according to Heisenberg, we don't know exactly where they are at all times or exactly how fast they're moving. And so what electron configuration is it's just a way for us to write out where or which orbitals the electrons of an atom might be found in. So if we're thinking in the biggest picture, you have the energy level, and then the next smallest level is the sublevel that has the orbitals that holds the electrons. So that would be largest to smallest. Okay, so if we are going to actually write out what we call an electron configuration, we're gonna fill up all of the sublevels and all of the orbitals with the maximum numbers of electrons, except for whichever one is the last orbital that you're working with, which will hopefully make a little bit of sense. So helium is right here on the periodic table, which kind of just covered up the 1s, but helium is in the first energy level. Its electrons are in an s orbital, and then 2 is the number of electrons in that sublevel or that orbital. So when we are writing configurations, you're going to see this notation repeated for however many orbitals that element or atom has. So the big one, or the big number, represents the energy level. The letter beside it represents the orbital or sublevel. And then the exponent represents the number of electrons. Let me make sure I forgot to scoot that up. All right, so now let's look at carbon. So carbon is right here on the periodic table. So we can count 1s 1 electron, 1s 2 electrons, 2s 1 electron, 2s 2 electrons, 2p1, 2p2. So let's fill that in one by one. So you've got 2 electrons in the 1s orbital. You have 2 electrons in the 2s orbital, and then you've got 1, 2 electrons in the 2p orbital. So that would be a total of 6 electrons. When carbon is neutral, it does have 6 electrons. So that tells us that we have the right amount of electrons. When we're saying maximum number of electrons except for the last one, 2 is the maximum number of electrons that an s orbital can have. So this is full, and then you do not have to fill up the last orbital that you're working with, because carbon only has 2 electrons in this p orbital. So let's think about magnesium 2+. If magnesium is right here, and if it's neutral, it has 12 electrons. But this is 2+, so it's gonna have 10 electrons. It lost 2 to now become positive. So if we go step by step, it's filled up the 1s2 orbital, it fills up the 2s2 orbital, it fills up the 2p orbital with 6 electrons, and then that's 10 total, 6 plus 2 plus 2. So this is going to be the electron configuration for magnesium 2+. If we look at bromine -1, remember there's an understood 1 there, even though it's not typed in, but bromine is right here. 1, 2, 3. And then if it's -1, really we're looking at it having 36 electrons. So it's gonna fill up the 1s2 orbital, the 2s2 orbital, the 2p6 orbital, the 3s2 orbital. We're gonna jump over here to the 3p orbital. It fills that one up, fills up the 4s2. And here's where we'll make a little bit of a note. Notice that we're reading this from left to right and then down one period at a time. The 4s orbital fills up before the 3d orbital. Charge and energy wise, it's gonna be easier for some electrons to be found in this orbital before they finish filling up all of the spaces in the 3rd energy level. And so that's why we see this kind of jump back in for the 4s and then the 3d. So no matter what, just read left to right and then down one row at a time, and you'll be fine. The other thing to note is that 6s right here fills up before 4f. Remember, the lanthanides and actinides scoot in right there, well, right here. And so you would have 6s and then 4f and then go back to 5d and then 6p. So don't forget, if we have one that is that large of an element, don't forget to include the F block. So if we're going back to bromine, we were at 4s2, we filled up that one, and then in the 3d orbital, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And then in the 4p orbital, because we gained 1 electron, it's going to be 1, 2, 3, 4, 5, 6. So 4p6. And then if we add all of these together, you've got 6 plus 10 is 16, plus 2 is 18, plus 6 is 24, plus 2 is 26, plus 6 is 32, 34, 36, and that's how many electrons a bromine -1 ion has. And then one last thing over here in this box, isoelectronic species are atoms and ions that have the same number of electrons, and so they're gonna have the same electron configuration. So kind of like we just did with this bromine -1, krypton is right here, so bromine -1 has the same electron configuration that we would write out for krypton. The other would be if rubidium right here, if it lost 1 electron, then it would move up or move backwards an energy level back down to be on the same energy level as krypton. So both of these ions would have the same electron configuration that the neutral krypton does. And that's what you need to know about electron configuration.